Hi everyone, this is the instructional video walking you through some of the important steps for the second lesson of the week 4 geospatial lesson, working through the RMD called Spatial Analysis. So we'll start by sourcing our setup script and then also loading in the spatial data you should have created and saved in the first lesson, Get Spatial. Okay, so the first lesson so far have walked through an introduction to spatial data, importing spatial data, and now this lesson is all about using both the SF and Terra packages for analyzing spatial data. So the first half works through some vector data analysis mostly, and then the second half will get into some raster data analysis and also working with both vector and raster data together. So first we walk through distance calculations. We'll set this T-map mode to view because we're going to plot some quick interactive maps. And first let's look at our occurrence data set. These are point data sets and we want to color it by species. So for this example, we want to calculate for each species, we want to compare their average distance to the nearest river. So essentially for each, we're working with our point data set and our rivers line data set. And for each point, we want to, one, find its nearest river feature and then calculate its distance to that feature. So each occurrence point will have a distance value associated with it. And then we'll do some data cleaning to calculate the average distance to nearest river for each species and find which species is found more often closer to rivers than others. And so the first step here is important is to look at the coordinate reference system. So what this section is doing is we're checking the CRS of our rivers and our occurrence data. Since we're about to do analyses with both of them, they need to be in the same coordinate reference system. And then based on if the CRS is different, which I will give you a hint, they are, complete this operation here using ST transform to set the CRS of the occurrence data to that of the rivers. And if you need a refresher on this, we did cover ST transformations in the week 1 spatial lesson. And so once we do that, now we can continue with the analysis. First exercise is asking you to notice that our occurrence data is across the whole state of Colorado, but our linear features, our rivers that we cleaned in the previous lesson was just Larimer County. So for exercise 1, we want you to explore the use of ST filter. You can kind of think of this as tidyverse filter, but for spatial data. So use your knowledge of working through inspecting a new function, see the arguments it takes, scroll down to some of the examples, and then what I want you to do for this exercise is filter the occurrences to just Larimer County. To get the Larimer County polygon, you can filter it from our county's object. And if you want to follow along exactly with the next steps, call this new object occurrence Larimer. Okay, so now for each point, like we said, we want to calculate its distance to the nearest river. The most efficient way to do this is using ST nearest feature function. So instead of calculating distance for each occurrence to every linear feature, we want to first find the nearest feature because we only need to calculate the distance to that. And so if we inspect so ST nearest feature, the first element is the point data we're calculating the nearest feature for, and then the second one is the feature data set to find the closest one. So for each occurrence, we want to find its nearest river feature. If we execute just this chunk, so when we execute st_nearest feature, just this chunk, it returns a vector of values. And what this is for each value, this is going row-wise through our new occurrence Larimer data set. And the value is the index or row number of the river feature that is spatially closest. So when we run this, we're creating a new column in our occurrence Larimer data set called nearest river. And where each value is the index number of the river that's closest. So now we have our closest feature. We want to use the st distance function to calculate the distance between the point and that nearest feature river, or nearest river feature. And we can index the nearest river feature with the value in this new column. And another note is it's important to add by element equals true because we want to perform this st distance row wise. So for each row, we have the point coordinate. We're pulling the nearest, the index number of the river feature that's closest, and we're calculating that distance. So we're creating a new column here. We'll call it river dist meters because it returns the value in meters. For our occurrence Larimer, so for each point here, we're calculating the distance to the feature here, and this is indexing. Remember indexing from the first lesson. This is a very fundamental skill you may want to keep going back to. But we're pulling out this value, which is the row number of the feature that's closest, and then keeping all of the columns. And then we tell it by element equals true to perform this row-wise. And it executes pretty quick. And now we see we have a new column called river dist meters, and this will be the distance of each species point to the nearest river. So now for exercise 2, this is asking you to do a little data munging of this new occurrence data set with this new distance column. And we want you to write some ggplot code to create this plot that is included in the lesson plan here. And feel free to add any more ggplot customization you want. But to answer this question, have the whole chunk of code you used to get here, including the data cleaning along with the ggplot code. And also pay attention to this hint here. Okay, next we're working with buffers. So next, say you wanted to know what percentage of a species occurrences were found within a specific distance of a river. So instead of calculating distance for each individual point, we want to know, for this example, let's say, what percentage of each species were found within 100 meters of a river. So this uses the stbuffer function. You'll notice you may not want to run this because it takes a long time. So what we tried here first was calculating a buffer, a 100-meter buffer around each river feature. But remember how kind of dense this linear feature object is. So that's why this is going to take a while. Alternatively, we can buffer points much faster. So instead, let's add a 100-meter buffer around each point, and then we can use intersecting to find how many of those 100-meter buffer points for each species intersect with the river. So it's kind of just an alternative way of doing it that's actually much faster. So we'll run this, and it still does take a little while. But next we're going to work through some intersects. So the function st_intersects, it will check for each point, but now we're working with the point buffers. So we'll notice in a second, occurrence buffer is actually now a multi-polygon object. For each one, it'll check, does it intersect with any feature in rivers? If it does, it will return, again, the index value or row number of the river feature that's intersecting with it. If there's multiple river features intersecting that buffer, it will return a list of each feature index number. And if there's if it doesn't intersect with any river, it will return a list of length 0. So let's execute this and inspect it a little further. So we called this river intersections. So again, this is a list, and what it returns is for each point buffer, the index number of the river feature it intersects. So in the first few we see here, these are empty. These buffers are not intersecting. If it has an index value, there's one feature that intersects that value. And then there's some where the buffer intersects multiple features, and it puts the index value of all features. So what we want you to do for exercise 3 is perform this st_intersects operation we just did, but add it as a new column in the occurrence buffer data set. And then we want me to create a new column that will return true or false if the buffer intersects with a river. And then there's this hint here to make use of the length function. So we're not interested in how many features are intersecting each point buffer, but we just want to know whether or not there was a river within that buffer. So whether or not there is an index value in that new column. And then second, we want you to calculate the percentage of occurrences that were found within 100 meters of a river for each species using some Dipler operations. So I helped to get you started here, but you'll notice that this doesn't totally work. And so to answer this question, we want you to figure out why this doesn't work. We'll give you a hint. It's just one line of code you need to add into the pipe operations to get this operation to work. Okay, second, let's give an overview of some raster analysis. Now we're working with the Terra package. So let's look at our land cover data that we should have imported at the beginning of this lesson. We see that it's a raster, but there are attributes associated with each raster value. So not only is each pixel, it is given a value, but that is the purpose of the auxiliary file, is it ties in the land cover category with each value. So we actually have some more informative legend associated. Instead of just seeing values like 1 through 250, we don't know what land cover class the values are. The auxiliary file ties in that attribute data for us. Okay, say we want to look at the frequency of each land cover type within all of Colorado. We can use the frequency function of the Terra package, and it returns a data frame giving us the value, so each land cover class, and then the count. How many pixels are that land cover class within Colorado? And then this next chunk is not an exercise, but it's a little challenge to turn this data frame into a ggplot bar chart. Okay, so this example, we want to look at some habitat characteristics for our species. Say we want to look specifically at forest cover, we want to calculate the average percent forest cover that each species occurrence was found at. This is just a raw categorical raster, so we need to do a few raster calculations to convert it to a percent forest cover layer. So first we need to reclassify. We want to turn this raster into just forest and non-forest pixels. So first we want to assign land cover to a new name to preserve the original land cover data. And then, since rasters are like matrices, we can index them similarly and assign values to specific pixels. So since we have these forest cover attributes tied to our cell values, we can actually filter based on those forest cover names. So what this is doing is within our new forest raster layer, we're indexing where forest pixels are in this vector of names. So wherever a forest is categorized as, or wherever a pixel is categorized as deciduous forest, evergreen forest, or mixed forest, we're assigning it a value of 1. Remember here, spelling is important with these land cover categories. And then second, for anything that is not a forest pixel, so now since we assigned everything that is forest as 1, we're indexing any pixel that is not 1 as NA. And so we can make a quick plot. Oops. Well, it's still plotted. You may get this weird error message. And it's not very pretty when we make this quick plot, but now every pixel value that is forest is given a value of 1, and everything that was not forest is NA. So now with this reclassified layer, we can calculate percent forest in a moving window, and this is called focal statistics. So there's a lot you can do with focal statistics, but here let's say when we say moving window, for each pixel, it'll calculate, we're going to assign a 9 by 9 kilometer moving window, remembering that our original resolution is 1 kilometer. So for each pixel, it will calculate this 9 by 9 window where that focal pixel is in the center. It will pick all of the pixel values within that window and then give that center pixel, the focal pixel, some statistical value based on the surrounding pixels in the moving window. And we give the focal function this information within the W argument. So if we look at this function, we're using focal as the function to calculate focal statistics. We're working with our new forest raster layer that is just forest or non-forest. And then within the argument W, we give it a matrix where the first value is the weight we want to give each pixel. Sometimes you might want to weight maybe pixels that are closer, a little higher than ones that are farther away. We're just going to weight everything evenly. And then the length and the width of the window, in this case, is 9 by 9. And then second is the function you want it to calculate within each window. We are going to sum, and then we also want to tell it to remove NA values, so it won't return any NA statistics if there was one pixel that had a missing value, which in this case it does because we assigned every non-forest pixel as NA. And so we're calculating sum because later, remember each pixel value is 1. If we sum all of the 1 values, and then later we'll divide by 81 because that's how many pixels are in each moving window, we can get the percent forest within that window for each focal pixel. And if we do the math with this, it's not exact because again these are squares we're working with, but this is about, say we're calculating percent forest within a 4.5 kilometer radius. So we create this new forest percent raster layer, and then we can perform math on the forest raster layer like this. Essentially we give it a raster layer and do some mathematical operation, and it applies this operation to each individual pixel of the raster. So raster math is pretty quick and dirty. So let's run this. Hopefully it plots nicely. All right, so if we compare this, this was just the raw forest or non-forest. But now we've kind of spread the values out because each pixel is now the percent forest within a larger window around that pixel. And if we compare the two, this looks pretty accurate. So a value of 1 means that there is 100% forest within about a 4.5 kilometer radius, down to 0 pixels that had 0 forest within that radius or moving window. Okay, so now we want to find out, we have our percent forest layer. So now we want to know for each species occurrence, the percent forest at that occurrence point. And again, double check before we do multi-spatial object operations that our objects are in the same CRS. Okay, so this first exercise here is telling us that we found out our objects were not in the same coordinate reference system. So exercise 4 is telling you to reproject our data so that the vector data, so the raster data is in the same CRS as our vector data. And so with this, we are going to use the project function from the Terra package. And then after you project it, write a line of code that double checks that our new projected forest layer is in the same CRS as our occurrence layer. And now that they're in the same coordinate reference system, we use the extract function from Terra. And this is a case where, for some reason, at least when I ran this, when I just used the extract function, it was pulling it from some other package I already had loaded. So this is a case where you need to use these double colons to specify, I want to use extract from the Terra package. And then we give it the, on the left is the raster we're extracting values from, and then on the right is the vector data, so the points we are extracting values at. And when we run this, oops, 1 second. Okay. I had to reproject the raster before carrying this out, and I will give you a hint. You also should use the Terra double colon before using the project function. So now when we run this, we'll notice that it returns a 2-column data frame where it returns all of it. On the left is it's giving an ID to each occurrence point it extracted the value from, and then it's giving us the value. So what we want to do, since each row is tied row-wise to each occurrence, we can, this next exercise is asking you to add a new column to our occurrence data set with this focal value returned. And a hint, this will use your knowledge of indexing. And I will also note that you did something quite similar back in the week 1 spatial lesson. And so once you have the extracted percent forest cover tied to your occurrence data set, so then you will know for each species occurrence what is the percent forest cover at that site it was recorded at. Calculate the average forest cover for each species and answer on average which species is associated with the highest percentage of forest cover. And then second, create a box plot to compare the spread of values for each species. So you'll have a box plot for each species representing their spread and average percent forest cover. And then finally here, that is one way we can use the extract function to extract raster values at points, but we can also extract raster values within polygons. and give it a function to how we want to summarize those values within a polygon. So let's go back to our land cover data. And for exercise 6, I've outlined the workflow, but to answer this, you'll need to fill in each line of code to complete it. So first, we want to project our land cover to the coordinate reference system of our county's shapefile. What we're going to do here in this exercise is calculate the most common land cover type in each Colorado county. So once we have our projected land cover data, we are going to add a new column to our county's data frame and call it common land cover. And so look into the extract function again. It's similar, but now we want to specify the function modal because we want to tell it, we want to extract our land cover from each county with the function modal. So it'll return the mode or the most common land cover value within the entire county for each county. So then you'll notice the output here returns the raw raster values, which aren't informative to us. What we want is the land cover classes. And this is where this auxiliary file comes in handy, because by reading it in with the auxiliary file, we have metadata tied to our geotiff, our raster file. We can use the cats function in Terra, and it will return this metadata, but we'll notice, so we have our land cover class. So we have open water, perennial snow ice, and what's really important here is the land cover class and then value. This is the raster pixel value. So these are the values that were returned when we performed the extract function. So the next part here is to use this metadata and use what you know of the left join function, and we want to tie each of our values that were returned here to their land cover class in the metadata. And there's also some hints here too. You'll notice that it fills in a row for each value from 0 to I think 250, but not all of these values have land cover classes. So you'll want to do some cleaning of this metadata file first. And then finally, once you have, for each Colorado county, the land cover class that is most common tied to it, make a map of these values showing the most common land cover type in each county, but use the class, not the value. This can be static or interactive, but it must include a legend, so we know that you properly tied the land cover classification to each value.